Thanks, Pooja, for starting the recording. If you guys can hear me, I'm on a train. Train going from Boston to New York. So I'll not interact much after this. Absolutely needed an interactive chat. But I'm very happy to introduce Professor Udit Bhatia. He graduated with a PhD from the SDS Lab several years back and has now been doing, I won't praise him too much, so fairly successfully as professor in the Institute of Technology, Gandhinagar, which is the IITs are one of the top institutes of technology, and IIT Gandhinagar is one of the up and coming doing things in general. And Udit is doing okay. He's actually been doing wonderful, as we see today, working both on climate and lifeline infrastructures and many other things besides. Very much, there are strong synergies around happiness, but he has been doing many things which go above and beyond. So we'll hear from him next, and Pooja. Coordination. I see Danish here. Danish is actually happy to join us as a PhD student. So he'll be a bridge. Next, overall, this is good. All of us are this and also for the dialogue. With that, we will see you going.
Thank you, Professor. And Udit, I think you can share your screen or anything. I think you have all the permissions. Yeah. You are mute.
You are mute.
Udit, you are mute.
It is one of those rare occasions when you are speaking and we cannot hear. You are mute.
Yes. Now I think I've unmuted myself, but are you able to see my presentation screen?
Yes, yes.
Okay. Because when I share, I cannot see what the viewers are seeing. I hope that the presentation is visible.
Yes.
And please point it to me at any point if my screen gets unshared. So should I start, Pooja?
Yeah, sure.
Okay, how much time I have? I want to keep it a bit interactive. So how much time I would have?
Yeah, it's till 12. Sorry, it's I think we have 55 more minutes.
Perfect. So I'll try to be on time and take questions as we go forward. First of all, hello everyone from SDS Lab, from MIR Lab, and students joining from the Dialogue of Civilization. I am Udit Bhatia. I am now, as Arup mentioned, currently I am working as assistant professor at Indian Institute of Technology, Gandhinagar. But I was at one point PhD student at SDS Lab. I was there at Northeastern University from 2014 to 18, where I was working on various aspects of network resilience and some aspects of climate variability and change. And during my time at Northeastern, I was TA for 1 year and co-instructor for 2 years for the Dialogue of Civilization courses. And of course, it was an experience, I would say, an overwhelming one, but an interesting one, where it was great learning curve for me to see the world as it is happening as we travel to Brazil, Singapore, and of course, India. So with that, I'll get started with my talk. I have kept it a bit broader at this particular stage. So people at SDS Lab, you might have seen some elements of the presentation in one of the earlier presentations I gave, but that was sort of a highly condensed version in 10-15 minutes. So I will have a glimpse of that particular work and a few more lines of work that my lab has been doing. Right now, as I mentioned, I have kept it a bit broader, but as and when we meet with the dialogue group in Delhi, I would love to talk about the specifics about any line of work that they are most interested in. And of course, I'll be also doing some hands-on tutorial with the students. So this is more of a movie version of the kind of things that we have been doing at the lab, and then we will have more hands-on detailed version. And I have titled my talk as AI and Data Science for Climate Resilience and Sustainability of Infrastructures. You may find certain elements to be really overwhelming because I've tried to put too much information in this particular deck of slides. But again, as I said, idea is to give you an overarching picture. So this is from where it started. This is a slide that I have stolen from my own thesis presentation that I gave at Northeastern University on 28 November of 2018. Where I was trying to put a lot of things that I was trying to do at the time of PhD into context. But as I'm progressing ahead in my academic career as a researcher leading a lab, all these things have started making much more sense to me, that why this is not a problem to be solved in isolation, but it's really a bouquet of problems that needs to be stitched together with some of the tools and techniques that I mentioned in the title itself, that is AI data science to solve the problems that we all care about. So if you see the impact versus likelihood plot that World Economic Forum publishes and updates almost every year, if you look at the top right corner, we talk about events which have high impact and high likelihood. And if you see most out of I would say out of 10 events that I have highlighted in the inset, 60 to 65%, 70% of them are related to extreme weather events, natural disasters, failure of climate change mitigation and adaptation, biodiversity loss and ecosystem collapse, and water crisis in some form. So they all are appearing to be very high impact, high likelihood, but what is important to understand that it's us means the people, the species, the ecosystems that inhabit this particular globe are being impacted. But the question is, what's the way out? That's where we started looking into the problem of going beyond risks. I understand many of our UG students might not be very much familiar, but generally speaking, risk is probability of hazard multiplied by vulnerability and multiplied by consequences. So basically it can be translated to a equivalent dollar value whenever things are tangible, that if certain events happen, how much we are going to lose. Of course, it's very difficult to quantify the human to quantify the cost of human lives and ecosystem services, but roughly speaking, risk gives us the magnitude of hit we are going to take when these high impact, high likelihood events strike the systems under consideration. So that's where we started saying that we need to also look beyond the risk and prepare for what is coming, how we should recover better, more efficiently, and in timely fashion, so that systems are back online when they are needed the most. So that's from where it starts. That is, we started looking into the systems at various scales, all the way from global systems to national systems such as US National Airspace, what we call as US NASAN, which is specifically focusing on civil aviation space, Indian railways and power distribution systems of India and within India, regional and mega urban setups like Boston, Brookline, and in India, Ahmedabad, Gandhinagar, and some of the cities that you are going to visit, such as Delhi. And finally, at the system level, that is, if certain events happen, are airports going to function? Are transmission facilities at localized level, which are being operated by a single facility manager, for example, Massport in Boston, and a state power distribution system in India, would they be able to serve the society when they are needed the most? So I will be covering some of these aspects in the case studies that I'm going to present, or in some of the lines of work that we are going to present. So one disclaimer is that I will be talking a lot about the work that we are doing in the lab. Perhaps it may not represent the most exhaustive list that about the work that has been done in this space, but this is I think I'm qualified enough to talk about the work that we ourselves are doing in much more depth and breadth. That's why I've chosen these lines of work to be presented here. So those who have visited SDS Lab, I know that a lot of things have changed now. SDS Lab is in the new building. When it was in the office space when I was there, we used to have a very nice poster somewhere near the screen where we used to have these two broad a broad vision of SDS Lab, that how we plan to connect the stress systems to stressors. After starting my own lab, what I call as MIR, Machine Intelligence and Resilience Lab, we started looking into the problems from a similar lens, but contextualizing the problems in bit better manner so that the solutions are more readily available to stakeholders. They speak to the local and regional problems while ensuring that science that we are trying to do, we are trying our best to advance the science, keeping the global aspects in mind. And that's where we try to translate these scientific gains or understanding that we gain in the context of hydrometeorological extremes. Under deep uncertainty, there are multiple sources of uncertainty, especially when it comes to climate change science. But how we can still leverage the data, physics, AI, combinations of data, physics, AI in the most synergistic manner to understand the risk and resilience of network systems, including Indian railways or Kerala, where you are going. We have done extensive studies in Kerala to understand how the floods and compounding hazards like floods and landslides cripple the economy of the state, one of the largest basins within the state every year, and what are the indirect losses that we get, and then translating some of the lessons that we learn at regional level to the local cities of Ahmedabad, which happens to be one of the oldest cities in India, which has mushroomed very organically, but now with fusion of modern infrastructures, roads, and high rises within the city, infrastructure finds itself choked almost every monsoon season because city was not designed keeping the current urban footprint in mind. And I'm using the word Ahmedabad here, but it would translate to many cities which have had the similar story of development here. And not only that, as I said, I mean, this planet Earth is meant to be shared by humans and ecosystems alike. And that's where we have, and this was one of the threads that I started during my PhD, but I finished um, uh, after starting the MIR lab here. So these are some of the three broad areas that we are pursuing at MIR Lab. One is resilience of infrastructure systems, network for sustainability and food security. This is something I would love to talk about because this is one of the most recent additions in our research threads in last few months. And then, of course, physics guided data sciences, machine learning for climate variability and change. Again, as I said, I don't over worry about the mathematics that you see or about the complex formulations, complex representations that you see. The most important thing here is story, that how we are trying to connect the pieces. So the first study that we did here was resilience of infrastructure systems, where we focused on the national scales. I will be using this particular figure multiple times to highlight that at what scale I've been talking about. One common thread across all the lines of work that I'm going to talk about, that all these problems are spatial in nature. In a sense, there is an aspect of space and time, or these are study done on spatio-temporal domain. So this is a common time slide that I would be using time and again. So again, if the prologue goes back to SDS Lab, in fact, this was core of my PhD thesis, where I was looking into restoration of networked infrastructure systems. By the way, when I meet the dialogue group during my in Delhi, I would be giving a hands-on training on how to generate all these beautiful plots and generate some of these graphical representation with much ease. So this was one of the first studies that we were doing, looking into that, can we really quantify the restoration of of infrastructure systems that are perturbed by events like tsunami or cyber physical attack or a power blackout that stems from shortage of water, which translates to increased load on the power distribution systems when farmers are turning on the underground water pumps to give water to their fields, but ultimately resulting in collapse of a power grid. Looks like the story of a thriller where all these things are happening, but these are the sequences of events that unfold many times whenever there is delayed monsoons in India. When you will come to India, especially people coming on dialogue, you will hear this word monsoon and how critical that is to keep the economy of not only India, but Indian subcontinent up and ahead. Then what we did is that we started looking into some of the more low likelihood but high impact events, that what if these failures are not isolated, they are not single point failures, but they are occurring multiple failures simultaneously at multiple points throughout the networks. Again, sounds bit like a movie script, but again, these events are no longer surprise in era of cyber physical attacks, where people with malicious intent, they indeed get control of the system and bring down systems at multiple points so that the recovery process takes much longer than anticipated. And that's where we find that most of the systems which sound to be too complex to handle, all of them offer us a region called as a warning region before they go into a point of no return or cascading failure. And we try to understand how wide or narrow this action window for us is, so that we can bring these systems down in graceful manner, what we call as gracefully degradation of systems, so that the restoration is easier. And we found that every infrastructure system, especially networked infrastructure systems, have this beautiful heartbeat kind of signatures which help us tell that when we are going from a green zone to orange zone to red zone, that is the zone of no return. And what we found is that not only these windows, they differ in size, of course, across the systems, but despite all the differences in complexities of the system that surround us, they have a signature or a universal patterns when looked from a mathematical lens, which tells us that while appearing to be a complex problem with so many components interacting with each other, there is always a way to analytically determine how we can gracefully degrade these particular systems before they enter into point of no return. This was all theoretical, looking into things in setting up the game by our own rules. But unfortunately, real world systems that surround us do not behave like that, because the systems are complex and the hazards or stressors that are imposed on the systems are also complex, as a result of which the analytical tools that we develop may not apply in entirety. So we started looking into that, how real world infrastructure systems will behave when real world concurrent hazards would hit them. So here, when we talk about real world concurrent hazard, we are essentially talking about, let us say that there are two examples. One is rainfall or precipitation extremes. There has been a lot of discussion that in warming world, we expect precipitation extremes to be more intense, and whenever they happen, they would happen with increased frequency. And we typically try to study these in form of what we call as intensity duration frequency curves or depth duration frequency curves. And there is a notion that in warming world, not only notion, there is a scientific proof. People have been looking into the thermodynamical and dynamical relationships between temperature and atmospheric processes, that these extremes are supposed to increase. But it's not the rainfall extreme that necessarily bothers us. It's the secondary effect that rainfall extremes or high amount of precipitation bring with that. One most obvious side effect is flooding, be it urban or be it non-urban flooding. Wherever there is an accumulation of water outside banks of the channels or where the water is meant to flow, we call that particular event as flooding. Does not stop there. Whenever there is long spell of flooding, or long spells of rainfall, they interact with the soil. When they interact with the soil, they change the properties of soil from dry to wet. And as you can imagine that a wet piece of soil would not be able to take the stresses or loads. Civil engineers typically use word load when in comparison to a dry mass of soil. And that's what we try to study for entire basin or a watershed in Kerala, where you would be heading. Whenever I'm saying you would be heading, I'm typically referring to the dialogue students who would be visiting Munnar, I think, where you would be going. That Kerala is known to receive notoriously high spell of monsoon rainfall over extended period of time, typically from July to September, and also early showers during the month of April and May. And being a mountainous area, it has lot of mountains with heterogeneous soil properties, which immediately change the load bearing capacity when they interact with the water. So what we did is that we reconstructed all the extreme events in 2018 for extreme rainfall and landslides that these extreme rainfalls will trigger with help of a slope stability model. And we combine it with our hydrodynamic model, which helps us do the flood assessments better. And interestingly, we have a basin which has city at its mouth and fairly unmanaged basin at the tail. What we found is that it is not the flooding that was causing the problem, because most of the flooding was concentrated somewhere towards the mouth of the basin, which is one of the largest cities, Kozhikode, here. And it was the combination of landslides and flooding somewhere in the remotest part of the basin, which was snapping this entire basin. If you see this particular figure E into two parts, where we were losing the connection between the more developed urban center, which was house of all economic activities, hospitals, schools, colleges, to the more distant parts of the basins, which were fairly undeveloped or underdeveloped, but are connected with one of the most important highways connecting these two part of the cities. And we didn't lose this particular highway until both of these particular events started happening together rather than in isolation, highlighting that how much power these models, be it dynamical model, hydrodynamical model, slope stability model, that encapsulate lot of equations of physics that we learn in our undergraduate programs, help us assess the risk better so that we prepare for these particular events better. And our key finding was that we were underestimating risk by 71% when we were considering these events in isolation. Unfortunately, these numbers get validated time and again, because this particular study was in 2018. In 2022, we have exact same sequences of events with different time windows, of course, but again, making this entire Perrier River basin fragmented into multiple points. As I said when I started this presentation, that I'll not be only talking about risk, I'll be also talking about what to do with risk. Yes, we understand that there is a risk. Can we really combine or assimilate the information about the people who are using these particular systems, for example, into these models, so that we have a socially or socio-economically aware risk management frameworks at place. This is one of the studies that we did for government of Gujarat during COVID times. If you remember, all of us were in lockdown. Authorities were absolutely clueless when to open, where to open the cities, how to lift the lockdowns, because the side effects of swift movement were too evident at that time. So it was sort of a juggling act where there were too many pieces to balance. So what we did is that we said that we can really look into some of these risk assessment models that we develop for these natural systems and combine the social data, that is how many people, households, most vulnerable population, people who are literate versus illiterate, rural population, people with disabilities, households without electricity, with the health infrastructure data at the finest resolution possible. What would be a county in US would we call as a district or taluka in India. So we tried to get all the possible data sets around the socio-economic indices for the two states, Maharashtra and Gujarat. Maharashtra where Mumbai is, Gujarat where I am currently located, with the capital at Gandhinagar. But both of these have large number of districts about which we obtained all the social data, health infrastructure data, and the current peril which was at play was COVID-19, that how many people are there and how many people have already deceased in these particular districts. And we combined all the information that we got here with our already designed risk assessment frameworks that we were developing for natural hazards to identify that what is that particular shortest route that connect two districts so that your risk of exposure while traveling is minimal as you go from point A to point B. As you can imagine, this immediately becomes a problem where you have to look into large number of combinations, because if there are n number of districts here and n number of districts here, you have to be mindful of all the connections within those n districts, within m districts, and mapping from n to m. As a result of which, what was appearing to be a really straightforward problem, that is, okay, we'll take a model from there and combine it with data we have, it immediately became a problem of dimension. But again, what came to our rescue is understanding of networks, representation of these systems as networks or graphs. I promise that when I meet you during dialogue, I would be giving you much more comprehensive hands-on understanding of how these tools work. But what this ends up giving us is that now this risk metrics tell us if I have to go from place A to place B, the shortest path that is most tempting from Google Maps or Waze is not necessarily the safest one. So I should not go with that one, but I should take a bit of a detour so that I am not exposing myself in a district which has high vulnerability because of already existing cases or poor health infrastructure and so on. Here, notion was simple. When you are traveling, especially when you are doing long distance travel, you would be taking pit stops, you would be taking fuel breaks, you would be taking food breaks and so on, as a result of which you cannot ignore the exposure that you will get during these pit stops. And that's what we put in the center of this particular framework. And this particular work is now published and available in one of the transportation journals. So coming from the risk assessment to risk management to the urban scale, that is, now that we were looking into these particular data sets, we collected a lot of data sets organically as we were fiddling to which data to use, which data not to use. And that made us wonder that we have been talking about risk, we have been talking about extremes, precipitation extremes, we have been talking about networks. What is the most organic way to put these things together to solve a problem for a city of Ahmedabad, which happens to be our hometown? Whenever it floods, the city chokes. I already gave the narrative. City not designed for population of today. Well-designed core, that is the older part of cities, was fairly well designed, surrounded by high-rise buildings. Core happens to be the lowest point. High-rise buildings happen to be at bit of a higher elevation. So whenever there is a downpour, all the water from these high rises, there is no intervention specifically. There is no green roofing, for example. There are no flexible, there are no permeable pavements. Most of the water finds its way to the older city. So and these cities are very, very difficult to reorganize or redesign because they are built of concrete. So there have been a lot of theories and postulates that, we should design infrastructure as green as possible. We should have green roofs. We should have flexible permeable pavements. Permeable pavements is something that would act like a sponge whenever it rains. But the question that we had from the Ahmedabad Municipal Corporation, the corporation, the equivalent would be the management of the city, that we don't have space to put all this in an existing place. So what we did is that we again brought our network model, along with our hydrodynamic model, along with our flooding model, to understand which particular part of the cities flood the most during these extreme events and how do they interact with existing sewage and stormwater drainage networks. Once we identified that, it became a problem of optimization where we have limited space and lot of green roofing or interventions to be done. So what we did is that we did quantification or sensitivity analysis in a realistic urban setting, that if we add 1 square meter of a particular intervention strategy, how much of peaks and extents of flooding we are going to reduce. And what we found here is that it would take immense amount of investments for green interventions in a constructed city, in already constructed city, because of its interaction with topography, that it may be a suboptimal investment to go to all these what we call as patching up of green infrastructures on already existing cities. Rather, the solution is to build green as we are building ahead, and to make sure that the conventional stormwater drainage systems are already in place before the monsoon start, if we really want to reap in the benefits of these green infrastructure investments. So the point here was that unless we bring all these models together in a way, the data sets together in a way, all the extreme solutions, yes, it seems to be fair enough to call for a system which has 100% of green roofing, but then comes the economic and financial and logistical constraints in the already urban spaces, which we help through these tools understand, make the stakeholders as well as people who are managing the cities understand. So if I talk about map of India, this is somewhere that Delhi is on the north, Kerala on the south, Gujarat on the west, and then we went to Odisha in the east. If you see here, the tools, the choice of methods, they remain similar. The only thing that is changing is the context, the kind of problems each of these regions face, but ultimately the thread is that all these systems are complex. They are being overwhelmed or perturbed by the natural hazards or disruptions, and all of them lose connectivity. And given the complexity, we don't understand where to intervene, how much to intervene, and how to intervene so that we recover faster, which again takes me back to the first point where I started my talk from, that yes, risk assessment is important, but what's next? So we did a very similar study with Odisha. Odisha is on the eastern coast, one of the states having highest socio-economic vulnerability index, but battered by cyclones originating from Bay of Bengal almost every year. And it serves as the entry point or gateway of many of the landfalls of the cyclones that originate in Bay of Bengal. And then once the landfall is made, these cyclones find their way from Odisha to West Bengal, cutting through the Bangladesh and so on. So these particular events, when they progress, cyclones would bring serious amount of rainfall along with winds and would disrupt power, transportation, and of course, livelihoods of many people as they progress. So what we did here is that we mapped all the power transmission systems that were damaged during one of the cyclones named Cyclone Fani. That was one of the most powerful cyclones that has hit the eastern coast in last 100 years or so. Once we mapped these dots, or what we call as nodes on the map, I brought this question to one of my colleagues in structural engineering, that we have been doing all these make and break arrangements with network science using node representation, edge representation. But first question that we should ask, why these structures even failed? If they are designed to standards, assuming that standards are complied for, assuming that wind speeds are within the design limits, why these failed? Before we even start talking about restoration, before we start even talking about hardening these infrastructure systems which collapsed, we have to understand what is the fragility of these particular systems. What I learned from my colleagues in structural engineering, that structural engineers love fragility curves for all the structures, components, elements that they design. They are typically governed by the fragility curves. But what is less known is that what if the nature of hazard or true magnitude of hazard itself is not known, and the extent of damage it will bring to infrastructure system is not known. These element level fragility curves become more or less useless. So what we try to do is that we try to develop the fragility curves for these individual towers and then map it with the same network science approaches that we have been developing for Indian Railways, US National Airspace, to identify where to hit the spot if cyclone Fani or 1,000 related events like Fani happens, because Fani is one of the instance. It's a stochastic process. You may have landfall at some other location and may cover the entire spectrum of state. And this particular study is got significant highlight from the stakeholders themselves, because as we were anticipating that when things get lost in complexity, so does the action. So it helped them identify what are the top 100 location of transmission towers that should be hardened before the next sort of cyclone season comes. Cyclone season means whenever the temperature differences within the oceans or the seas become more significant. So that's where this particular work helped us make an impact. Now, as we progress ahead with water, we get more questions than answers. For example, when we were dealing with Ahmedabad, when we were dealing with Odisha, when we were dealing with Kerala, what we realize is that yes, big picture is great. If you recall, I started from a national scale. I came to a regional scale, then I come to a 2-state scale. Now I'm coming to then I came to a city, and now I'm talking about a particular channel where water is flowing. Because when you talk to stakeholders on field, they use a word called as adaptation a lot, right? In dialogue, you will hear two words, mitigation and adaptation, many times, right? Manage what you cannot avoid what you cannot manage, from adaptation to mitigation. And in existing cities, in existing urban ecosystems, stakeholders typically use the word called as adaptation. Let us manage what we cannot avoid. Yes, we are in bad spot given all the changes, warming, discussions around warming, and now we have to act. So the question is how much we should act. So one of the motivating example here was how we should design in the floodplain. Interestingly, most of the large Indian cities, like many cities in US, have a river flowing through their heart. So Ahmedabad, for example, has river Sabarmati. Delhi would have Yamuna. And if you go to Kolkata on the eastern side, you would have river Ganges cutting through the city, and I'm sure same applies to many of the cities, because that's how many of the civilizations originated. But the problem here is that now we have unchecked construction in many of the floodplains without realizing when it floods what it means for the critical infrastructures located in these floodplains. Yes, we can definitely keep a check on new sanctions on the projects that are going to come. What about protection of existing infrastructures? It's very difficult. It may be very easy for us to do all what if scenario generation theoretically, but when you talk to stakeholders, they would tell us the problem is much more complex on ground. It's a problem of equity, it's problem of rehabilitation, it's problem of displacing the entire community that has been living at those particular places for years and perhaps centuries. So it is not the problem of just shifting things here and there, and we have limited to no understanding how these interventions or adaptations will interplay with reducing overall vulnerability to flooding. So one of my students, Ashish, in my lab, he started looking into coupling hyper resolution hydrodynamical models with the with various adaptation strategies like dry pond, filled up pond, dry pond with vegetation, and trying to understand that where we would stand in this particular decision matrix of not adapting to flooding, to over adapting in flooding, and what are the changes that we would be able to see if we adapt in certain way than the other, and how the overall profiles, the hydrodynamic profiles of flow changes under various intervention strategies, and what is the relative reduction in magnitude of velocity, peak flows, and inundations as and when we go with one choice versus the other. Again, the point that we were trying to make is that sometimes stakeholders may not be interested in pinpoint solution. They may be interested in understanding what are the options they have. And then depending upon the overall budgetary constraints and logistical constraints, which is the option to go to, while understanding the trade-offs associated with each of them. Again, I'll not go into the technical details, but here what we see is that now we understand what is the cost is to benefit of all these adaptation strategies in the context of complex river geometries, confluences, when these interact with the urban settings that they meet as they flow downstream. So as we have been doing all these works with built infrastructure systems. This was a realization long back when I was doing PhD and took a course with Professor Tariq Govier in Department of Ecology. And I was really impressed with the kind of things I was not aware of that surround us and we take so lightly. So one classic example is bees, honeybees, right? You might have been seeing a lot of memes and tweets these days that if honeybees go extinct, we all would run out of food. I used to laugh at that particular statement that, you know, how insignificant all these statements are, unless I really started looking into the complexities and the webs that these ecosystems build around themselves and how the failures cascade. And then what we did is that we studied around 30 ecosystems across the globe of various size and magnitudes, impose the dynamics. I was talking about hydrodynamics. Interestingly, hydrodynamics are two coupled nonlinear differential equations, what we call as Sand-Winand equations. We have very similar equations in ecosystems, what we call as Lotka-Volterra models, plus in the sense that they come up with their own adaptations in terms of representation of interactions. But the beauty is all these systems are dynamic, all these systems are nonlinear, and all these systems are coupled. And that gave us an entry point into understanding the resilience of these systems, combining the lens of networks and dynamics to understand what is the best way to restore particular species when ecosystems are perturbed to certain magnitude, and can we really identify a winning strategy to maximize the restoration gains. Now the broader question arises, in case of flooding, it's very clear we want to reduce the extent and peak of the flood. In case of landslides versus floods, we want to minimize the disruption. In case of power transmission, we want to minimize the time it would take to bring light back into the electricity back into the city. Here we found that ecosystem also have services to deliver. They have to ensure that they persist. They have sufficient abundance to carry out their ecosystem services, and they are stable. They are not fluctuating and ultimately die out. So these are the three competing and sometimes complementary attributes that we kept track of while simulating our dynamical system to identify what works and what not. So talking about networks, talking about food, talking about complexities, what we have been also recently looking into is that whenever there is a network, there is movement of goods, there is movement of products across the systems. So what we did is that, again, when we go into the mine, sometimes we end up with gold, sometimes we end up with nothing. And as we keep on collecting these data sets, talking to various stakeholders, which is very difficult task to do, believe me. Yeah.
Udit, can you hear me?
Yeah.
So we here the slides almost jumped from 21 to 25. Can we just quickly show 22, 23, 24?
Yeah, sure. So, perhaps there was some lag because I was showing this slide. Can you see slide 23 now? Is it visible? Okay. Yeah. Yeah. Pooja, can I go ahead now? Is it visible?
Yes, yes.
Yeah, so I'm deliberately not going into the results part right now because it would take much long of a time, because as I said, I want to convey the idea of the breadth. But this complexity food brings us to our next case study on understanding that how these trade networks fuel the overall food security in the context of India, where we were looking into mapping all the commodities that get exchanged in India, be it agricultural, non-agricultural, over past 10 years, and using again the same network lens to understand who is feeding whom in terms of interstate or intranational trade activities that are going within the country. What we found here is interesting. That is, as we can expect, as GDP is increasing, agricultural trades are increasing, non-agricultural trades are increasing, certain aspects of networks are changing, certain areas are getting more self-dependent, other places are getting more over-dependent on the other regions because now they have more money to purchase the things. What is most interesting for us is to translate all these understandings of evolution of attribute of trade into what it means for the producing states. For example, Punjab and Haryana, known as bread balls of India, they have fertile land. They are land to 5 rivers, now technically 3 rivers after partition in 1947. But that's how Punjab gets the name. 5, Punj means 5 and Ab means river, land of 5 rivers. And of course, it was super fertile land, fueled the green revolution in India, which made India self-reliant in production of all the staple crops, including wheat and rice. Despite highly complex and convoluted economy, India more or less enjoys almost 100% self-reliance in production of staple crops, that is wheat and rice, which itself is sort of an accomplishment of green revolution, given the investments and modernization that went into agricultural practices some 30 years ago. But we wanted to translate that what it meant for states of Haryana and Punjab in long run, because the networks are at play. Kerala may be importing wheat and rice from Punjab and Haryana, while Punjab and Haryana will get money for that. The land pollution stays back in Punjab and Haryana. The use of fertilizers happen in Punjab and Haryana. Percolation or leaching of micronutrients and macronutrients happens in Punjab and Haryana, which have not been quantified for last so many years since Green Revolution started. So again, we brought our dynamical model. Again, the dynamical model borrows the elements from hydrodynamics and ecosystems, but with a different context. Help us understand how much we are retaining back, how much we are transporting, because if we apply 100 grams or 100 units of any fertilizer, only 30 to 40% is actually utilized by the plant and remaining goes into the soil. Some of that is recycled back, some of that becomes part of the water stream, which ultimately influence the water quantity as well as usable water quality, usable water quantity and water quality attributes once the leaching happens. And what we found here is that the volume that Punjab, Haryana, Chhattisgarh, and in some cases parts of Andhra Pradesh, which were sort of surprises for us, are retaining translates to teragram of nitrogen and phosphorus per year that just get retained because of interstate trade that is ongoing for last so many decades, powered by the Green Revolution. Again, this was interesting for us because we have been talking about greenhouse gases. We have been talking about loss and damage model in almost all these big meetings that happen at at the negotiation tables. People who are in dialogue, they will hear all these terms, loss and damage, IPCC, and various agreements that people that various countries get into as they negotiate through their development plans and so on. So I'll not go into details, but what it brought to our highlight is that what we are missing is a very big piece of what is happening within the nation across the states, but overstressing certain parts of the nation versus other, resulting in unsustainable food practices, which may have significant consequences when it comes to the food security of the nation. So again, we started from the networks, brought in dynamics, and solved a problem which appears very different. But now that when we look into the choice of tools that go into, all of these are ultimately related with the same three words: dynamics, networks, and complexity. Finally, how we have been using, so this was more of the application part. One of the most important threads that I've been enjoying a lot is looking into developing these models from scratch. That is looking into that, can we really bring machine learning, physics-based models, physical models, models inspired by LLMs, large language models like graph neural networks, into improved understanding of hydrological processes and understanding of extremes, where we have been looking into, can we improve the overall state of the hydrological modeling itself, where we want to translate the rainfall to stream flow and then ultimately flooding. Although I skipped that entire connection when I was talking about Kerala, that okay, there is a rainfall, there has to be flooding, but that translation itself does not happen that easily. It has to be processed through multiple steps, lot of abstractions, lot of uncertainties become part of this entire stream. And that's where we have been trying to leverage the power of physics and power of deep learning or machine learning to improve the overall state of understanding of process representation within these hydrological models. Again, I will not go into details of this particular model. This particular work is published and the related work is under review, but on archive. So please feel free to read that, and of course would love to discuss as and when we meet. But what it tells us is that the power of physics and machine learning, when assimilated together in a synergistic manner, help us address many of these limitations at certain cost. There is no free lunch theorem. But ultimately, it gives us a very, very powerful framework to bring together the stressors, the resulting uncertainties, and resulting policies that govern these systems into making the reliable decision making, to ensure that multi-sectoral aspects are taken into account as and when we are talking about water allocation problems and so on. Again, I'll not go into the detailed methods, detailed framework. I will share these slides with Pooja. Pooja, please feel free to share these with the audience here. Most of the work here is either archived or published, so feel free to share with the people here. And another thing that we have been looking into is that now we understand so many things about the flood and its associations, how these extremes are changing. We have been hearing this word climate change, extremes are getting more extreme and so on, but an umbrella statement may not help if we really have to bring machine learning models, improve predictability of processes in improving the overall schema of things. So what we have been started looking into is that how these rainfall extremes have changed over last 100 years in the context of Indian subcontinent, and then specifically in context of India, because we want to ensure that there is security. We want to ensure that the adaptation strategies are best informed. And these are the areas, the spatial coverages we are talking about is huge. So can we really identify the pockets that, despite all the non-uniformity and variability, in fact, this was Professor Ganguly's one of the earlier papers in 2014, where they said in Nature Climate Change that Indian monsoon has increasing variability and non-uniformity in last 100 years or so. So here we try to investigate that despite all these changes in variability and non-uniformity, can we again leverage the power of networks to understand how the underlying networks are changing? So what we found is that despite increase in non-uniformity, increase in intensity, increase in duration, frequency, the underlying network structures are much more stable than we originally thought. With strong localization happening in central India, central eastern India, where Odisha is located, making these particular regions the first candidates where adaptation and planning should start, because for last 100 years, while we see certain oscillations, these red dots tend to cluster back again in central India while ensuring consistent signatures of remarkable stability across various network attributes, making these particular regions the center of synchronous extremes. That is, when extremes happen, they happen synchronously in this particular region. And this brings me back to the first slide, that is MIR and SDS, that this is how we are trying to leverage the power of machine learning, data, physics, hydrodynamics to understand the problems of past, present for better future. These are some of the work that is in news, and of course the volume of work that I presented, I have an excellent team here working on various aspects. Danish, who is present here, would be joining SDS Lab soon. So this entire work on monsoons and stability on synchrony is Danish's brainchild. And these are some of the publications. Again, I'll share the list and slides with Pooja. If somebody is interested in any specific part, please feel free to read them and go ahead. And these are some of the collaborators with whom we have shaped this work. So Pooja, over to you. I know it was overwhelming, but I thought I should give a full view of the problems.
Yeah, thank you so much, Udit. It was hard to believe that like this amount of work came out from one lab. Hello.
Yeah, Pooja, thank you. And of course, credit goes to all the lab members here who are also present on the talk, on the chat, by the way. So I'd love to have any questions, generic, specific.
Does anyone have any questions you can ask?
Hi, Udit.
Hi, Ashish.
Thank you. Amazing talk and literally a lot of things you are doing. So one quick question about you mentioned in slide number 11 that the graceful restoration of systems or graceful failure of systems. So can you please explain a little bit like how does that work in terms of, let's say, in the context of a urban rail metro system or the US Airways system? How does that look like, and if there is any way to simulate that from a regular failure or regular restoration, what to do so that,
Yeah,
yeah.
I think this is an excellent question. So what here we mean is that, we have a system which is having large number of components interacting with each other, right? Let us say there are 1,000 nodes and 100,000 edges. So what we see here is that every system has a heartbeat, and we can translate that in form of functionality, connectivity, and so on. So on a typical day when everything is fine, you would expect this heartbeat to be much more stationary, opposite to how biological systems behave. But what happens is that as you start losing functionality at a single point, what you would see is that at certain points there would be certain drops or slight spikes coming in, but it may not bother or overwhelm the entire systems, and people would typically perceive these as local failures happening somewhere in some part of the network, which should automatically correct or should be taken care of. But what we see here is that as this spike continues, there is a region where these spikes suddenly grow in size much more than the initial spikes. What we call as and we use the techniques of single differentiation, double differentiation to identify the sign and changes in sign itself, to identify where the magnitudes are changing dramatically in these heartbeats of these infrastructure systems. And what we find here is that when we look into first derivative of functionality and second derivatives of functionality, there comes exact signature points when there is zero to mild change and then mild to drastic change. And that's what we are saying, is that these are the regions where you should either bring entire system offline, do the restoration or fix the failure, rather than waiting for entire failure to propagate and then rebuild from the scratch. Now, depending upon the context, here we did it for Indian Railways and US National Airspace, the definition of functionality itself will change. But again, what we hypothesize here is that most of the systems, as we did simulations on real world and synthetic networks, that all these systems do exhibit the heartbeats. And most of the complex systems are somewhere positioned between truly empirical Barabashi-Elbert models versus realistic Indian Railways or US National Airspace, which are nothing but combinations of different distributions coming at play.
So in addition to that, one more quick question. So is there a real way to validate these type of things, like unless this type of failure doesn't happen in real life?
Yeah.
So that's, I think it's a bit challenge to validate these type of stuff. If
Initially, I was thinking so that it would be very difficult. So our first study was completely theoretical, but when we got the real data of Kerala, that is Periyar River Basin, we can easily see these failures or the heartbeats. And I'll just quickly share my slide here. I hope it is visible. So
yeah.
So this was all theoretical, as I said, but we were able to trace exactly similar signatures with real data. This is real data. There is no theory involved. But we were able to see the similar signatures, but much flatter signals, not as dramatic of heartbeats as we saw here, perhaps because of the size and topology of the road networks itself. But yeah, those signatures become evident, especially if you see the regions around this, where we suddenly have changes in the first derivative and second derivatives. So there is indeed a way to validate it. But again, these are data intensive. You need great cooperation from stakeholders, because all the studies that I'm showing, they are powered by a lot of data that comes to us from stakeholders, from field survey. I have one student, Ravi Raj, who travels for months to Kerala just to collect data, talk to them, convince them that, today it may appear to be a fruitless exercise for you to share data with us, but you will thank us 5 years, 4 years later. And that's how we are running the show.
Right. Amazing. Yeah. Thank you so much.
Any other questions?
Yeah, any other question? So while we wait, I have a quick question as the hydrologist or hydrodynamic person in my earlier history. So I am saying that you are using 2D hydrodynamic models or combined with hydrologic models in lot of your problems to delineate the flood and then imposing it onto the networks. So are you using the traditional ones, or do you have your own work on those as well? Like what kind of models are you using?
Yeah, so that's again a very good question. We have been using suite of models depending on the context. For example, when we have been looking into Kerala, there is a lot of satellite products that we get, which are much easier to assimilate into state-of-the-art models, including HEC-RAS, for example, including Mike plus Urban, Mike She. And most recently, the work that I was showing here, all these models are developed from scratch. So Ashish in my lab, he writes all the, syntax and codes in various FEM suites that are available in combination with ANSYS fluid flow, which are, I would say, are more primitive, but gives us much better control over smaller domains. So it is a problem of scale, basically. When I have to address to a problem where the scale is as large as Kerala or India or entire portion, I just cannot have these FEM based models do reinvent the wheel. So I would focus more on insights here. But when I'm looking into the interaction, fluid infrastructure interaction, I cannot take the elements or changes in momentum, flows, depths for granted. And that's where I go back to basics and try to develop these models from scratch. In fact, at IIT Gandhinagar, we have some of the excellent courses in transient hydraulics, where my students have been learning how to write all these packages from scratch, and I'm really proud of things that they have done as part of these courses also.
Yeah, that's what I was also thinking. Like seeing at the figures and the work that you are doing, it's not always easy to do in the traditional HICRAS or HICHMS. So
Exactly.
you might have done something different here. Yeah.
Yeah.
So do you have any other questions? We are past 7 minutes, but I think we can take 1 or 2 questions. No one? Okay, then I guess thank you so much, Udit, for this talk, and it was really insightful for all of us. And it would take us months to go look for all the papers and all the figures that we have generated in this one slide. So thank you so much. I will share this with everyone else, and the people who were not able to join this, I will send the recordings to them also. And yeah.
And I look forward to meet the team during your time in Delhi. And thank you.
Yeah, I'll definitely schedule 1 full day of your class so that I also
Absolutely.
get to learn. Yeah, thank you so much. I think Professor Ganguly is not here with us anymore, so I'm just saying bye on behalf of him. Bye, everyone. Thank you.
Bye.